Ladies and gentlemen, welcome back to another video. And in this video, we're going to be continuing with our series on space, time, and motion. So I'm going to be picking up from where I left from the equations of motion in the video I made on space, time, and motion. In this video, however, we're going to be talking about momentum. Now, a lot of people are familiar with what momentum is, but we're going to be looking at it in a different way. And the way we're going to be looking at it is through Newton's lens. Now, a lot of people might not be familiar with this, or a lot of people might not know this, but Newton never called it momentum. This is our modern term. Newton never called it momentum. What we today call momentum, Newton back in the past called the quantity of motion. Now, this at first sight might not be very intuitive because you might be very used to using the term momentum. But contrary to what you may think, the term quantity of motion or the phrase quantity of motion is actually the more intuitive term, the more natural term when it comes to dealing with physics. So in this video, I'm going to be unveiling how we should now view momentum as the quantity of motion. I'm not saying we should change the term momentum. Whenever we hear the word momentum, whenever the word momentum is spoken of, we should always bear in mind that we are relating this to the quantity of motion. It makes more sense, and I'm going to be showing you why in this video. So let's get into it. Okay, so a good understanding of the concept of momentum in physics will help you very much in understanding Newton's second law. Now, let me just write this on top in case I might need to refer to it. So we've got this on one side, and we've got this on the other side. So this is Newton's second law in just the ordinary vector form, and this is again the ordinary vector form, but with a bit of calculus. Okay. But I'm just putting this in case I might need to refer to it as we progress. Now, why did Newton view momentum as the quantity of motion? In order to really see this better, I want us to first begin with a particle, not a huge rigid body, but a single particle. Let's picture a single constituent particle and say this is it. It might be spherical or whatever, it doesn't matter. We're not concerned with the geometry of the particle, but we just want to start with the idea that we've got a particle. So say we've got our particle. Now, if you watched my video on space, time, and motion and Newton's second law, you might remember the fact that whenever a force is imparted on a constituent particle, a velocity, an accompanying velocity, let's call this F1, an accompanying velocity, I'm calling V1, is imparted on the particle. In the very instant, the same instant we impart a force of F1 is the same instant we get a velocity of V1 on the particle. So if we exert a force of V1, the particle will get, or a velocity of V1 will be imparted on it. So, but if you really want a clear understanding of what I'm talking about here, visit my video first on space, time, and motion, and check out my video on Newton's second law. So if you remember, we said if you exert a certain force, that force brings along with it a velocity, and we're calling it in this case V1. Now, remember that this is a single constituent particle. It is not a body. It is not a huge mass. It is not a rigid body, if you will. So it's just a single constituent particle. Now, I'm going to refer to this equation now. Not this, but this. If you substitute 1 here in Newton's second law, if you substitute 1, what you mean is, in this case, I'm neglecting the fact that the units of mass are in kgs. When you substitute a value of 1 for m, in the smallest scale of units possible, remember, I said I'm neglecting the fact that we might use SI units here, which are kgs in this case. So if you substitute a value of 1 in the smallest scale of units possible, what you would have done is you would have this, what you get after substituting, this means that whatever system you're dealing with constitutes of a single particle of matter. I think we mentioned that you should see the video on weight and mass, the difference between weight and mass. I think I mentioned this in Newton's second law. Just take a look at the videos. So what happens here, the moment you substitute 1, that means in your system, like at the smallest possible scale, what you are dealing with is a single constituent particle, which is what we have in this case. Okay, so let's say this is a timeline. Now, if this doesn't make sense to you, if what I'm saying right now doesn't make sense to you, please watch my former videos. Space-time in motion, like that one is very crucial. Space-time in motion in Newton's second law. Because I apply a theory that you might have never seen before. A theory I discovered while studying physics. I do not know if someone else discovered it, but it helps you understand things better. Okay, so this is a timeline, and I'm just going to put our symbol there for T. I'm not going to put the units, any units you have, any units you may think of, sorry. But I usually work with the smallest possible units for time, possible, and I call those units in terms of time, part time. Okay, so let us assume that our constituent particle over here, during the first instance in time, which is 0, we've labeled it as 0. Let's assume that during this instant of time, or instance in time, this particle was at rest. There was no force acting on it, no net force whatsoever. Say a force of F1 is then introduced. Now, keep in mind, during the first instant in time, or instance in time, our object is at rest. That instance in time is 0, our object is at rest. We then introduce a force of F1. Initially, our object is at rest. With respect to this timeline, our object is at rest. And then afterward, a force of F1 is then introduced, meaning that our force of F1 is associated with this point in time, not this one, this one. Say the force F1 introduced, which caused a velocity of v1, this velocity which has been brought about caused the constituent particle to move from this point A to this point B. And say this is 6 parts in length, 6 part lengths, part length being the smallest unit of length possible. So what happens is, remember, this happened in a single instance in time. So what it then means is the velocity v1 is actually equal to 6 part length per what? Per part time. This is a part time, the smallest unit of time possible. This is a part time. This is a part time. There is nothing in between here. Remember, there is nothing in between. There is nothing in between. This is not continuous. It's discrete. The timeline I'm using is discrete and not continuous. So if our object, after introducing a force of F1, is moved from point A to point B, and we measure the length between point A and point B and find it to be 6 part lengths, then since we know that this was introduced in a single instance in time, and we haven't moved to this part of the timeline, we can then conclude that the velocity imparted by the force F1 is equal to 6 part length per part time. Now, listen to this. Now, the velocity, this velocity is what Newton referred to as the quantity of motion. I'll repeat, this velocity is what Newton referred to as the quantity of motion. As I explain, you understand better why he chose the term quantity of motion. Couldn't he have thought of a better term? You understand why he chose the term quantity of motion. So, number one thing to keep in mind as we move along now, this velocity That is, now, listen to this. It does not matter if the force is present or not. Say we exerted a force of F1, and then in the following instance in time we removed the force F1. We know according to Newton's first law that our body will continue to move with a velocity of 6 part-lengths per part time in a linear fashion. It does not matter that the force F1 is no longer present. The body will still possess a quantity of motion of 6 part-lengths per part time throughout its entire course, as long as no external force comes into play. The body will continue to possess a quantity of motion of 6 part-lengths per part time. Put this one into your mind. Whenever you come across the velocity now, always think, but this only applies to this single instance. Whenever you encounter the term velocity associated with a single point, I'll repeat, not a mass like a huge mass, or a huge body, but a single point. Whenever the term velocity is associated with a single point, that is a point that represents a constituent particle. I'm not talking about those cases in physics where you have where they tell you that, okay, let's assume this is a point mass, but the point mass weighs 5 kg. No, that's not what I'm talking about. I'm talking about an instance where the point genuinely represents a constituent particle. So when you have a scenario where you've got a point that represents the smallest particle of matter possible, its velocity is referred to as the quantity of motion. If the velocity of a single constituent particle is being referred to as the quantity of motion, what about a scenario where we have a mass of say 5 kg?